DJ, my friend, we're up and running. Okay, fire pump. Fire pump voltage drop. Fire pump voltage drop. I have my beautiful fire pump sitting in here. Right here is the overcurrent protection device for it, at least the first overcurrent protection device. We're not going to get into sizing the overcurrent protection device yet. We will get into sizing overcurrent protection device. The only thing I'm worried about right now is the distance between this and this is actually 300 feet. And this boy is 50 horsepower motor. 50 horsepower motor. And 50 horsepower motor. And the voltage at this is 208 volt. It's a 208 volt and it's three phase. 208 three phase 50 horsepower motor that runs a pump, a fire pump. And I need to size the conductor. Code letter, I want you guys to add that term. Code letter. Let's make it a code letter K. In the code letter, let's N. Just make it a code letter N. Code letter N. Okay. What I need to do is the following. Here's what I need to do. I need to size conductors. Number one, voltage drop, based on voltage drop. Number two, continuous load. Number three is voltage dip. Voltage dip, voltage drop, continuous load. Three calculations. And guess, guys, which one are we going to choose? Anybody can guess? The one that gets you the largest conductor. The one that gets you the largest conductor. Voltage drop, continuous load, voltage dip. I'm going to write a few articles so you don't have to argue with Chad and say we don't believe you and you brought this stuff from your grandma's basement. For voltage drop and dip, you're going to go to article 695.7 NEC. For continuous load, we're going to go to article. So when I do the calculation, Ryan, my friend, you're not going to say, Chad, why did you multiply by this? If you say, I'm going to refer you to this article. And we're going to go to article 695.6C2. And all of them are NEC code book. Okay, let me repeat myself. When we do the calculation, the first one and the last one, voltage drop, voltage dip, we're going to do them based on these two calculations. Going to be based on NEC 695.7. If you guys go to the NEC, it tells you for voltage drop fire pump, you can go 5%, and if it's a dip, 15%. Everybody knows what the difference between a drop and a dip. Drop is constantly, the voltage drops constantly as long as the pump works. A dip is momentarily drop in the voltage for 10, probably 6 to 10 seconds until the pump come up to speed and pick up the load and run. Okay? Drop is constant drop of the voltage. So you lose 5 voltage constantly as long as the equipment works. Dip, only momentarily drop in the voltage at the time the fire pump starts, mostly for 10 seconds. Most of the time for 10 seconds, the voltage dip. After 10 seconds, it goes back to the voltage drop. It dips all the way, and then after that, it goes back to the voltage drop level. So the dip is momentarily. And if you guys would write to yourself 10 second drop, 10-second voltage drop only, 10-second voltage drop only. At start. That makes sense. 10-second voltage drop only at start. Right? That's it. That's what voltage dip is. Okay, we set the criteria. Did we set the criteria? We set the criteria. That's example number 1 and the lonely one that we're going to do probably. Any question, guys? So we're going to go size 3 things and call it a quit. Everybody knows we're getting the information from where the NEC code, we're getting the information. What's a drop, what's a dip, what's continuous load. Everybody knows what continuous load, right? 3 hours or more at full current, full voltage, full current. That's what we could, at full current. The voltage usually stays the same. Code letter N. Pay a lot of attention to code letter N. This info is given. All this info right in here is given. All right, let's go ahead and start sizing. Anybody has an issue about the given? What are we given and what do we need to find? Everybody knows what are we? Yes, Ben, my friend.
I was just gonna say we're given the 50 horsepower.
Yep, and the voltage, and the phase, and the code letter, right on the nameplate. All this information given. This is given. Given info. All this information given. What do we need to find? At this point, we need just to size the conductor. Later on, guys, we're going to be sizing a lot of other stuff for the fire pump, but for the time being, just conductor. All right, let's go. Let's go ahead and start. Number 1. When we start number 1, what did we call number 1? Is it a voltage drop or voltage dip? I want to start, as a matter of fact, I want to start with the one that continuous. Was it number 2? I will start with number 2. Number 2, continuous load, as a continuous load. Okay, I have a 50 horsepower at 208 at 3 phase. What's the full load current from table 4? 30.250.
143.
Is it 250 the table?
Yeah.
Chad, you're genius. 250, 143, 143 amps. The table is right off, 250. Okay. Then, everybody knows it's a motor, guys. We find the full load current of a motor from table. If it's 3-phase, 430.250. If it's single phase, 430.248. Spencer? More or less. Okay, now, then you take the 1.25. Why 1.25? Because the code says that. Which code? You've already got it written. 1.25 times 143 equal. Who's going to get the 10 points? 178.75.8. 178.8. Huh? 10 points. 10 points.
It's working.
Giving the momentum here.
Let's say he gives all 9.
Now DJ lost 2 points just by not being here. Okay, then we're going to take this beautiful amp cable all the way to which table, Mr. Erbab? 310.16. Soon to change to 310.15 B something. Okay, table 310.16 under which column and why?
75 more.
75. It's more and also it's higher than both, higher than 100 amp, and also it's motor. So what would you get there? How many conductors? 3 conductors, and what's the size? 3 aught. Okay, 3 aught. What insulation? We'll leave that for another time. For fire pumps, you need a special type of installations. I lost 2 points just because of hee hawing around.
Yeah. Right, I'll gain it there. No.
Any question, guys? So what we did, DJ, my friend, we just sized a conductor for a motor based on continuous load. We have done that multiple times. We haven't started the stuff, the voltage drop even. Any question, guys, about number 2? So number 2 gave us a size of 3 aught. Let's go to see what we sized based on number 1. Number 1. So number one, voltage drop sizing. Voltage drop sizing, guys, I want to use voltage drop equal 1.73 times rel R I L over 1,000, and I need to find R so I can size the conductor. Now remember, if we're finding R, we find the conductor with the smaller R, the next smaller, or the next higher. When it comes to R, the next smaller, because smaller R, bigger conductor. This is a tricky one. So I'm going to flip the formula to find R equal 1.73 times, R equal voltage drop times 1,000 divided by 1.73 times I times L. If you don't know how to flip the formula, go back to Mr. Kildrick, Mr. Ryman. Attitude Chad has, huh? Everybody knows how to flip this formula, guys? Did I flip it right? Or do I have to go to Mr. Ryman too? No?
Probably should.
Okay. Now the voltage drop. You guys okay?
You gonna go fight them?
But they're nice guys, I know. Okay. Now remember, voltage drop 3%. Now voltage drop for fire pumps are allowed to deeper to what? 5%. So voltage drop here is volts, not percentage. So here's 0.5. Why 0.5? Because it's fire pump. Otherwise, it would be what? Would be 0.3 times what's the mother source voltage that we're running this motor at? 208. 208 times 1,000. What's 1,000, Brad? 1K. Smart Alex Chad, huh? Times 1.73 times what's the current? We found the current, didn't we? What was the current for this? Since we don't know the nameplate current, if we know the nameplate current, we stick the nameplate current here. We don't know the nameplate current, so we're going to use the code current. What was it? 143, right? Times what's the distance? Was it 300? 300 times 300. And if you do your math, you get, I need R. R is going to be small, so don't be scared if you get it in a decimal R. R is small. And I need two gentlemen or two ladies. We don't have two ladies, a lady and a gentleman to agree. How much? 1.4. 1.4 stands until I hear from another lady or a gentleman. 1.4. Okay, 1.4 stands. What's ohm? 1.4 ohm. Now, what does that mean? I need a conductor with 1.4 ohm or less, not more. Did you come up with something different?
No, that's right.
1.4 or less. So where do you go to find the conductor, guys? So 1.4, take it all the way to chapter 9, table number 8. What do you guys get? I need 1.4 or not more or less. How much? Under copper, uncoated. Number 8. Number 8.
It should be a 10 or something.
It should be 0.1. Should be 0.14.
Oh,
Yeah.
0.1.
Should be
Is it
0.14.
0.14 or 1.4? See what? 0.14. And we moved away with that one, huh, guys? That's what I thought. It's a little bit small. Okay, 0.14 agreed. All right, so let's go to 0.14. Take it again to chapter 9, table 8, in NEC code book. Everybody knows NEC code book, right? That will give me what? How many conductors?
1
3 conductors. Number 1 aught. Agree with DJ? Okay, 1 aught. 1 aught. Okay, so the first calculation gave us what? What did we get from the first calculation? 3 out? Did we get 3 out from the first calculation? So what does that mean? This one is already dropped because it's less than the first calculation. So I'm going to drop this calculation. Everybody knows why I dropped it? Because it gave me a calculation less than what normally I need to size the motor. So anybody knows why we guys came up with a small conductor here? Because when we size the continuous load 25% extra amps. That's a lot of amps. Spencer, my friend, you couldn't find it? 0.14?
I'm a little behind.
Okay, I'll wait a little bit. 0.14. Now, I want you guys to write next to this 0.14 or less. You need 0.14 or less. Why less? Because if you go more, that's a smaller conductor. Less R. What does less R means? Bigger conductor. What does more R means? Smaller conductor. So 1 aught. Why did I drop the 1 aught? Because the first calculation gave me 3 aught, and I'm supposed to do 3 calculations. Pick the one that gave me the largest calculation. Okay. Any question guys before we do the last calculation? Spencer, Arab, my friend. Still, did you find the R? Okay. But do you know why less? Because if you go higher, if you're a conductor of 0.14 or larger R means a smaller conductor. Smaller R means bigger conductor. I know that's up and down, it keeps confusing. Leave some for Chad, will you? Keep stealing my coffee. Any question, guys? All right, let's go to the last calculation. So we know, everybody knows why I dropped 1 aught. Smaller. Okay, let's go number 3 and the last one. Voltage depth. For the voltage depth, here's what we need to know. For the voltage depth, here's what you need to do. First, find the locked rotor current or starting current. We need to find locked rotor current. Locked rotor current, or another fancy name for it, starting current, or starting current, another fancy name for it. Okay, to find the locked rotor current, here's what I need to do. Locked rotor current, to find it, you need to go to table 430 dot, what is it?
7B.
7B, thank you. 430.7B, as in boy, table. And keep in mind that the motor that you're dealing with, is the voltage is 208 volt, and the horsepower is 50, right? 50 horsepower, and it's a 3-phase. All this, if you guys go to table, which we've been there, 430.7B, it tells you to calculate the locked rotor current. All what you need now, locked rotor current equal, what's the multiplier? First of all, what's, and also the code letter, what's the code letter I gave you guys? N. For code letter N, guys, what's the multiplier?
12.49.
12.49, the largest, the highest, 12.49. So I found, let's do it a better way. Based on all this, N equal 12.49. Anybody does not know where I came up with 12.49, and that's directly from 430.7B, and N will equal a multiplier of 12.49. Now I need to find the locked rotor current. Any question at first, all this is just to find the 12.49 based on N. Where did it get N from? Nameplate, on the nameplate.
Why do you go to the highest one?
The worst scenarios.
Oh,
The worst scenario.
every time.
Unless you know otherwise. It's kind of cover yourself type of design. Okay, locked rotor current, then here's the formula. since it's a three-phase 1.73, we need lock rotor current. Let me write it again. Lock rotor current, the horsepower times M is the multiplier, which is coming times 1,000. This is the formula we'll be using, divided by 1.73 times the voltage. And some of you are going to ask me, what the heck is an M? Is the multiplier which is coming from directly from this table. In my case, it's a multiplier for N. M is the multiplier for N, and it's 12.49. M. I just call it multiplier M. That's the formula that we're going to use. We know the horsepower, we know the voltage. We know if it was a single phase Brooks, what would you do with the 1.73? Chop it off and open the window here and throw it out the window. If we hit somebody in the head, we're insured. Okay, let's plug in the numbers. Plug in. My horsepower was 50. Why? Because Chad says so. My multiplier is 12.49 given because my code letter is N. And what's the 1.73? 1.73 is 1.73, Chad. And what's the voltage? The voltage is three-phase 208. Three-phase 208. Did we miss anything? I have the horsepower, the multiplier. Oh, the 1,000, Chad. Don't miss the 1,000. 100. By the way, the 1,000. The reason why the 1,000, because if you look at the table, the multipliers are given in case. If you read the top of the table, guys, the multipliers are given in case. What a K? A K is 1,000. So that's why you have to multiply 1,000. I need a gentleman and a lady, or two gentlemen, to agree on an answer. Or DJ and two gentlemen. 17? 1735 M. Anybody disagree or agree?
Agree.
Cool. M. 1735 amps. 1735 amps. Okay, so that's step number one. We need to find the lock rotor current, the starting current, the inrush current. All these fancy names for inrush current, start current, lock rotor current, fancy names for the same concept. You energize a coil, huge amount of energy need to energize it to start the spinning of a motor. That's now, what's the next step? Take this amps, slam this amps right into the formula for voltage drop or voltage dip, and size the conductor based on the lock rotor current. What we're trying to achieve here, Ryan, my friend, we're trying to make sure, as we dip to pick up the load, as we dip momentarily for 10 seconds to pick up the load, the voltage dip is not going to be lower than 18% of the voltage because of the size of the conductor. As we start the motor for 10 seconds, the voltage is not going to dip more than 15% of the nominal voltage. As we dip. Did I say it differently?
Yeah.
The first time?
Yeah.
Okay. Now the second time's right?
Second time.
As we dip. That's why now when we dip for start, when we start the motor, guys, we don't use the full load current because that's not what you start with. You start with the starting current, a huge amount of current. That's why we did the calculation here, because we always start with a huge amount of current because of error. Long story short, all what you have to do is just use this amps now in the second calculation. That's where we came up with this amps. Why I can't use the 163 Holly, my friend, because the 163 is a full load current, not the starting current. Okay, I want somebody to remember 1735, and go to the second calculation. Then the same thing. We need R equal voltage drop times 1,000 divided by can you guys give me the 1.73 times the amps times the length, right? Yes. I always know it as voltage drop. Okay, did I miss anything? Okay, you guys are cool. Okay, now which amp we're calculating the voltage dip? that we're sizing the conductor based on the voltage dip. That's what we're doing. To size the conductor, I need to find R. Okay, so I have a point. What's my multiplier for the dip?
15.
15%, which translates into 0.15 times, what's the voltage? 208 times, what's the 1000? 000, divide by 1.73 times. What's I? I is the locked rotor current. What was it? 1735. 35 times, what's the length? 300. Does that look like 300, DJ? Not to me. Times 300. Times 300. I need a gentleman or a lady to find an answer here. You come up with something? You can throw on the board. 0.035. Anybody came up with something different? Same? Brooks? I need another one. I don't trust Brooks. Same? Okay. This is a big number. 0.035. Okay. Then we're going to take the 0.035 all the way to chapter 9, table 8. What do you get? Or less. Can I ask or less here? Or less. So we go down. Or less. Or less. Or less. Brooks? 400 kcm. 400 kcm. How many conductors? 3 conductors. Number 400 kcm. Anybody came up with something different? 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 Okay, now what did we find for art? That's a big difference, huh? And the difference because I use, guys, a multiplier that's really n is big. So in a case like this, which conductor are going to be using then? 400 kcm. We went from 4 aught. Was it 3 aught? Was 3 aught? Then 4 aught one step, 250, 3, and 350, right? We have 350 all the way. So 4 steps higher. So which one am I going to stick with? Use to size feeder. Right? Because it's the largest. And use, I'm going to write myself a note here. Use the largest of the 3 calculations. You're going to use the largest of the 3 calculations. And in this case, the largest of the 3 calculations, right, that we did end up 400 kcm. Any question, my friends? So I'll go back and dropped one. I'm going to drop the second one, right? The 3 aught. I'm going to drop the 3 aught. Why did I drop the 3 aught? Because I have a bigger calculation than a 3 aught. Bigger calculation than a 3 aught. Any question, guys? Any questions?
The question is on this calculation, which is 0.15 times 208 times 1000 divided by 1.17. Isn't that 17.35? Isn't 17.35?
Did you miss 2 digits? Like I usually miss 1 digit. You missed 2, Mr. Rebel. Did you miss? When we did the calculation for the amps, let's go back to how we calculated this. Did you multiply by 1000? Probably that's where your mistake is. Did you multiply the top by 1000? See if you missed 1 digit like I do all the time. You missed 2. That will make me feel good. Any question, guys? Any questions?
Can you go back to the last page?
Sorry.
I'm just trying to.
There you go. That's all I have for today. We're gonna do advising after lunch. 11 o'clock. Who is A? A would be Mr. Yeah, I think Muhammad is the first, no?
Yeah.
And then the rest of the day, guys, we will be doing working on our projects. Just FYI, tomorrow is the last day of the week for us, our academic week. So I want you guys to print everything full, complete set. Wednesday, by Wednesday.